Scalability sits at the center of cloud architecture and capacity planning. It runs through two pillars of the AWS Well-Architected Framework. Those are performance, efficiency, and reliability. This is from systemsarchitect.io. Subscribe to the channel and like this video for more great cloud tips. Scalability is the practice of designing systems that absorb rising load by adding resources. That load might be requests per second, concurrent users, or bytes of stored data. Adding resources means one of two things, and the difference matters enormously. You can scale vertically, giving a single machine more CPU, memory, or storage. You can scale horizontally, adding more machines that share the same work. Both paths apply to simple auto-scaling groups and to complex sharded databases. A scalable system keeps its response time steady as that load climbs. So what does an unscalable one do? An unscalable one rarely slows down gently. It falls over all at once. Thinking about scalability early keeps applications responsive as traffic grows. You avoid the sudden outage when demand spikes past a single server ceiling. You also avoid the opposite mistake, paying for idle capacity all year round. Matching capacity to actual demand is one of the largest cloud cost levers. Scalability decisions also get made early, and they are expensive to reverse later. A partition key is painful to change once you are at scale. So is a session strategy. Getting it right shapes your instance types, your data layout, and your deployment topology. Get it right and a growth spurt is a good day. Get it wrong and it is a very bad one. Horizontal scaling adds identical instances behind a load balancer. Each new instance takes a share of the incoming work. This is the default answer in cloud systems, and for good reason. The ceiling is very high because you can keep adding machines. Vertical scaling instead replaces one instance with a larger one. You move from a medium instance to a large, doubling CPU and memory. It is far simpler because the application itself does not have to change, but it usually needs a restart, and every instance family has a maximum size. Most real architectures use both, scaling the database up and the web tier out. Stateless services scale out far more easily than stateful ones. A stateless instance holds no data that another instance would need. Any request can go to any instance, so adding one is trivial. So what breaks when the service is stateful? Stateful services keep session data or local files on one specific machine. That machine becomes special, and specialness is the enemy of scaling out. The standard fix is to push the state into a shared store. Sessions move to Redis or DynamoDB. Uploads move to object storage like S3. Instances then become interchangeable and disposable, which is exactly what you want. A load balancer is the front door that makes horizontal scaling work at all. It spreads incoming requests across every healthy instance in the pool. Health checks are the half of this that people forget. The balancer probes each instance and stops sending traffic to the failing ones. Without that, scaling out just spreads your errors around more evenly. Connection draining lets in-flight requests finish before an instance is removed. That small detail is what makes scaling back-in invisible to users. Learn more at systemsarchitect.io. Like and subscribe to the channel and playlist. The database is usually the hardest thing in the system to scale. Read replicas are the first step and often the cheapest win available. Writes go to the primary, while reads spread across the replicas. Amazon Aurora supports up to 15 read replicas in a single cluster. This works well because most workloads read far more often than they write. Sharding is the next step, partitioning data across multiple independent nodes. Each shard owns a slice of the key space and scales on its own. Your choice of partition key decides whether load spreads evenly or piles up. A poorly chosen key creates a hot shard. No amount of hardware will fix it. Auto-scaling policies watch a metric and change capacity when it moves. Target tracking is the simplest form and usually the right default. You name a target, such as 50% average CPU utilization. The group then adds or removes instances to hold that number steady. Request count per instance is often a better signal than CPU. Scaling also takes time because new instances have to boot and warm up. That delay can run from tens of seconds to several minutes. So good policies scale out quickly and scale back in slowly. The cheapest capacity is the work you never do at all. A cache layer serves repeated reads without touching the backend. A CDN does the same for static assets out at the edge. Both cut the load you would otherwise have to buy machines for. What about a sudden burst of writes? Queues handle the other half of the problem by absorbing spikes. A burst of writes lands in the queue instead of overwhelming the database. Workers then drain it at whatever rate the backend can actually sustain. That turns a traffic spike into a slightly longer wait rather than an outage. Capacity planning means knowing your expected peak before it arrives. Account limits and service quotas are a real ceiling worth checking early. Autoscaling cannot launch instances that your account is not allowed to launch. Load testing at the expected peak is the only way to really know. You should also decide what happens when demand goes beyond that peak. Graceful degradation means shedding optional work to protect the core path. Turn off recommendations, serve a slightly stale cache, queue the non-urgent writes. A system that degrades on purpose beats one that collapses by accident. Performance holds steady because response times stay flat as concurrent users increase. Reliability improves because no single machine is a permanent bottleneck. A failed instance gets replaced automatically instead of taking the service down. Cost optimization follows from adding capacity only while it is actually needed. You scale in overnight and stop paying for machines nobody is using. Operations get simpler because scaling groups react without anyone being paged. Future-proofing is the quiet benefit that pays off a year or two later. The same architecture absorbs next year's traffic without a redesign. Aggressive horizontal scaling is not the right answer for every component. Some legacy applications assume a single machine and simply break across several. Tightly coupled databases that need cross-shard transactions scale poorly. They also cost real engineering time. For those, scaling vertically first is usually the cheaper and faster path. But vertical scaling has hard limits. It also creates a bigger single point of failure. The largest instance available is still one machine, and it can still fail. Over-provisioning for a rare peak is the third mistake worth naming. If the spike lasts 10 minutes a month, rate limiting is cheaper. So is a queue. Scalability remains a core requirement for any cloud system that expects growth. Designing for it early prevents expensive rework once the traffic actually arrives. Apply this when you pick instance types. Apply it when you choose partition keys and set auto-scaling rules. Well, that does it for now. Hope you got something out of this video. Find a lot more articles and guides on both systemsarchitect.io and codeguides.io. That's systemsarchitect.io and codeguides.io.